Okay, let's talk about the exam. So our exam number 3 is Friday. Again, we're going to start at 8:45 a.m. There are study sessions, review sessions today. 3 possibilities instead of recitation. So there's no formal recitation today or Friday. So these study sessions are available to anyone. Okay? So today, in Wexler 109 at 10:30 and at noon. So during the normal recitation time, instead of recitation, it's an open study session for anybody. And that's with LP. And then later tonight, in Wexler 303 at 5:30 with Jason. They're not going to get up on the board and work a sample test. They're just going to be there to help you. You can study in groups, and then they'll circle around and answer any questions that you have. And then if there's like some consensus on something that's difficult, they might do some on the board where a lot of people are struggling with. Okay, but it's a group study session with one of your TAs there to help you. That's what it is. Okay, so in terms of the exam itself, let's talk about that. If you go to exam prep and homework solutions, there's some suggestions for what to study or resources. So all the lecture videos, your notes from lecture. This is going to be, so what I emphasized in lecture is going to be what's predominantly on the exam. So don't go to Khan Academy because that may be somewhat helpful, but they may be emphasizing or going to talking about things that we didn't, okay, or emphasizing a certain way that we didn't. So I suggest you really focus in on what we emphasized in our lecture. So I gave the lectures, I wrote the exam, okay? Web work sets that are covered would be 14 through 21, and then any associated written homework and quizzes along the way. Okay, and then I gave you another list of review problems. Everything here is really important, good practice. For the most part, this is I'm pretty sure this is comprehensive, but in a second here I'm going to give you an outline, a bullet outline. But the ones that are bolded and underlined are more conceptual questions, and those are important, right? So I'm going to ask questions that see if you really understand series, see if you really understand sequences, not just convergent or divergent, which is important. A lot of the test is analyzing series for convergence, divergence, and the reason behind it. But then I'm going to see if how much you understand as well, stuff that we emphasize. So let's give a rundown here. Okay, so you need to analyze sequences. So we'll say understand. You don't have to write this down because I'm putting this on Blackboard as we speak, okay? So understand and analyze sequences. Determine if they're convergent or divergent. Okay? Understand and analyze non-alternating series. Okay? Determine if those are convergent or divergent. And what did we look at for those? We looked at geometric, P-series, comparison test. What else? The divergence test. Those are the main things we looked at for non-alternating series. Okay, so understand and analyze non-alternating series, determine if they're convergent or divergent, and then cite a reason. Is it geometric? Is it p-series? Using the comparison test, the divergence test. Okay, and then what's next? Alternate. So understand, analyze alternating series. Determine if they're absolutely convergent, conditionally convergent, or divergent. Okay, so what do we have for that? We had the alternating series test. And the ratio test. Okay, but the divergence test came into these as well. And the ones, so the ones we looked at before, comparison, divergence, those came into play also when we had alternating series. Okay, next is evaluate geometric series if they're convergent. And then we saw examples where you had to change the form. So you had to initially get in the form of you had to do some algebra, using laws of exponents to get it in the AR to the N or AR to the N minus 1 form initially. So you got to know how to do that. Okay? What else? So you got to know the divergence theorem. So relationship of sequences and convergent series. This relates to the divergence test. You got to know this inside and out. When we started talking about series, this is what I emphasized on 2 different days, and then we kept talking about it. This is like the most important thing about series is if you have a sequence, when does the series converge, right? So what does the sequence have to do for the series to converge? So what does the sequence have to do for the series to converge? What is it? The sequence must go to 0. If the sequence goes to 0, then does the series converge? Maybe. Some of them do, and some of them don't. So the divergence test says that if the sequence goes to a non-zero number or diverges, then what about the associated series? Diverges. You need to understand why, though. So you need to think about what's happening as you're adding up the terms of an infinite sequence. Whose limit is not 0. Why does the series converge? You got to understand that. Not just memorize the divergence test, but understand what it's about, why it's true. And we worked on that. We worked hard on that. Okay, we worked hard on that. Okay? So understand all aspects. Of previous sentence. Understand all aspects as the relationship of sequences and convergent series or divergent series, etc. Okay, so there can be stuff about that. Okay, so you need to know how to build a series for a function related to the form a divided by 1 minus r. So we spent a couple days on that, and then you just had your web work due today for that. All right, use the ratio test to analyze power series. Find the interval and radius convergence. I think that's it. So the Maclaurin and Taylor series will not be on this test. They'll be on the final. So what we started Monday, that Taylor and Maclaurin, and we'll do a little bit more today. You'll have web work on that due Monday. It'll be on the final, but it won't be on this exam. Okay? Okay, so this is it. This is on Blackboard in that same post. The same post, Exam 3, April 8th, in what area is this? Exam Prep and Homework Solutions. Exam Prep and Homework Solutions. You've got the study resources, and now the skills and concepts list. Any questions on any of these? That's the exam. There's nothing on the exam that's not on that list. Okay. So and then you got the help sessions today. The help sessions, and then all the office hours tomorrow. So you got a full day of office hours too. Most of us have office hours. Check the schedule all day long. Any more questions on the exam? We will meet here 8:45 on Friday. Let's check out web work. Let's see here. So number 20. How do we do? Is this the one? All right, so it looks like number 3 is a good one to look at. Awesome. Good example. Okay, let's look at this one. Arctan, so we want a function for arctan of x over 12. A function for arctan of x over 12. Okay, so is there something like a over 1 minus r related to this? Is there something like a over 1 minus r related to arctan? And what is that? What is 1 over 1 plus x squared? Okay, so the derivative of arctan is 1 over 1 plus the argument squared. Okay, and so that's a lot like 1 over 1 minus r. So let's start with that. So if we call, say, f of x, if we call that 1 over 1 plus, now we want this exact argument here, so x over 12 squared. then we know that in general, if we took an antiderivative then of f, we would get arctan or something very close to it that we could clean up and fix, so that that's exactly what we have. So let's write we're going to write the series for this, and then we know by taking the antiderivative, we'll be in the realm of arctan x over 12, and we can finish it. So what is this? This is 1 minus the opposite of this thing squared, right? So our a is, so we're going to go n equals 0. A value is 1 times the opposite of x over 12 squared. So that's our a is 1. Here's our r squared. Now, what I recommend here is, since we're going to be dealing with antiderivative in x, isolate the x part. Isolate the x. Pull this apart so that we got x by itself. It's going to make life a lot easier.
Wouldn't it be to the 2n?
Yeah. To the n, right? So that thing, this is squared, and this is to the n. Sorry, thank you. There we go. The r value is the opposite of x over 12 squared, and then it's r to the n, right? A to r to the n. Remember, if this starts at n equals 1, then your exponent has to be n minus 1, so that the first exponent is 0, right? So whether it's n equals 0 and n equals 1 and n minus 1, the first, for a geometric series, the first exponent has to be 0. Okay, so let's isolate everything. So what do we have? First thing we have is just a negative 1 to the n. And then we have 1/12 to the 2n and x to the 2n. So I'm going to split up the negative and the x and the 1/12 all separate. So I'm going to have 1/12, that's to the 2n, and then the x to the 2n. And this is going to be very convenient when we take the antiderivative. Questions so far? So that's our geometric power series for 1 over 1 plus x over 12 squared, because this is actually minus negative. Let me change that. 1 minus negative. So that's our r. In the brackets is the r value, and so then I took that r value to the n. Good so far? Okay, so now we're ready, and I also recommended that you write out the terms. I ran out of space, but do it over here to the right. Write out what that thing means. Write out each individual term. It's a good way to check and make sure you got the antiderivative right. But plug in n equals 0. Plug in n equals 1, plug in n equals 2, n equals 3, write out those first 3 or 4 terms, and work on that too. All right, so now what are we going to do? We're going to do antiderivative. Antiderivative of, I want to change it back to 1 over 1 plus, because that's a lot easier to see there. So we're back to 1 over 1 plus x over 12 squared. So it's the arctangent of x over 12. But now we got to think, this is kind of like, but it's x over 12, so it's like undoing the chain rule. We're going to take the derivative of arctan x over 12. Do we get exactly this? So it's going to be 1 over x over 12 quantity squared. Then what? Times the derivative of the interior by the chain rule. So times another 1/12. Do we have the 1/12 there? No. So what do we need so that when we take the derivative of this, we get exactly what we started with? Divide by 12? Multiply, right? We need another factor of 12, so that now when we take the derivative of that, we get exactly the function f, this one. So there's our antiderivative of f, 12 arctan x over 12. So let's write out what that is. I'm going to go right to this one. This is why we did this. So what's the antiderivative of this series right here? N equals 0 to infinity. Anything that doesn't have x's in it just comes along for the ride. Nothing changes. So we're going to just keep it as it was. Negative 1 to the n, 1/12 to the 2n. Now here comes our antiderivative. Antiderivative of x to the 2n is x to the 2n plus 1 over 2n plus 1. Now, we just took an antiderivative, and so up to this point we have not taken into account something that we should have. What happens when you take the antiderivative of a function? There's something we haven't considered before that we should consider now that we have now that our feet are wet. Yeah, so when you take an antiderivative to get the function, we could have any constant, right? So there's a plus c. You can have any constant added to it. When you take the derivative, you're going to get that original function because that derivative of that constant is 0. So when we take antiderivatives, we need to add on that constant. Now, for our purposes, for getting your problems in web work, this didn't matter. But really, it's an important point that we need to remember that we have a constant of integration. We have to account for that. Okay? Okay, so now, is this series now the series we want for arctan of x over 12? No, it's 12. This is 12 times arctangent of x over 12. So to get arctangent of 12, what are we going to do? Multiply by a 12th or divide by 12. So we're going to take, we need to multiply this series that we just got. We got to multiply by 1/12 so that we are left with just arctan of x over 12. That was the function we wanted to write as a series. So I'm going to start that in red so we can distinguish here. So arctan of x over 12 is equal to. So what happens when we take 1/12 of this function? Every term will be divided by 12, and so we can just adjust that right there. What will that become if every term is divided by 12? How many 1/12ths will we have now? Instead of 2n, we'll have 2n plus 1 more, right? So we'll have negative 1 to the n. 1/12 to the 2n plus 1 times x to the 2n plus 1 over 2n plus 1. All right, and what happens when we divide a constant by 12? We just get a different constant, right? We just get a different constant. So you can call it C1. Okay, so it's just the old constant divided by 12. That just gives us a different constant. 1/12 of the constant we had before.
So you can find the constant right there.
What's that?
You can find the constant at the end of those things, right? If you substitute in x equals 0, then the summation goes away.
Okay. Okay, so to find the constant, we can find it when he's saying when x equals 0. So if we plug in x equals 0, or any value, but 0 makes it easy, Do that up here. So do that in blue. When x equals 0, we just get all the terms are 0, right? Because when x equals 0, this is all just 0. It's going to be 0 plus C1. And what is the arctan of 0? So what are we saying is we're saying what angle gives us a slope of 0 between negative pi over 2 and pi over 2? So between negative pi over 2 and pi over 2, what angle gives us a slope of 0? That's what we're saying by that right there. And it's the angle 0. Okay, it's the angle 0. So 0 equals 0 plus C1. So the constant is 0. So then we got it. If we want to write the first such and such non-zero terms, so when n equals 0, when n equals 0 is the first non-zero term. If you plug n equals 0 in there, you get 1 times 112 times x. So the first non-zero term is when n equals 0, you get 1/12 x. And then n equals 1, you're going to get negative 1, 1/12 cubed over x cubed over 3. So that'll be the next non-zero term. So we can just generate the non-zero terms by letting n be 0, 1, 2, 3. What about the radius of convergence for this? So you're going to use the ratio test. Use the ratio test. And you can get the radius of convergence. All right, questions on this example? Did it help? That was the lower success problem. So there's lots you got to know. You especially have to be good at your laws of exponents, changing things around inside and working correctly with the sequence that you're summing up in terms of laws of exponents, algebra, chain rule. So doing these derivatives and antiderivatives often involves chain rule. You got to be really, really good at that.
Would you be able to run through the ratio test?
What's that?
Would you be able to run through the ratio test?
Yep, we can do that. So the ratio test, get up here. Okay, so here we go. So we got 1/12 to the, it's going to be 2n plus 3 times x to the 2n plus 3. So when we do n plus 1 and you multiply that out, you're going to get 2n plus 3. So this is a of n plus 1, right? A of n plus 1. When you plug n plus 1 in to 2n plus 1, so 2 times n plus 1 plus 1 is going to be 2n plus 3. So I did that 3 times, right? I did that 3 times. And then times an, or times 1 over an, which is going to be 2n plus 1 over 1/12, the 2n plus 1, and x to the 2n plus 1. Okay, so if this is some other number besides negative 1 to the n, like negative 5 to the n, you got to include that because that's going to give you a value. But if it's just negative 1 to the n inside the absolute value, that will go away. But if it's anything else, like negative 3 to the n or negative 10 to the n, make sure you don't just eliminate that. That will give you a value in there, okay? But just negative 1 to the n will go away in the absolute value. And so what I'm left with here is, we're taking this limit as n goes to infinity. So we got the 2n plus 3, 2n plus 1 over 2n plus 3. That will just be 1. And how many more 1/12ths do we have on the top? 2 more, right? So we're going to have 1/12 squared. There's 2 more 1/12 multiplied together here than here. And then how many more x's? 2 more, also x squared in the top. And so that limit as n goes to infinity is going to be this right here, because 2n plus 1 over 2n plus 3, that limit is 1. So we're left with the 1/12 squared and the x squared. And that has to be less than 1 for convergence. So we got x squared over 12 squared. Is less than 1. And so basically, so x squared is going to be between 12 squared and 0, right? Because if you're squaring it, it's automatically positive, right? So it's between 0 and 12 squared. So that means that x could be anything between 12 and negative 12. Right? Because if you square anything, square any number up to positive 12, it'll be less than 12 squared. Square any number as low as negative 12, that'll be positive and less than 12 squared. So our interval is negative 12 to 12. The radius is 12. The radius is 12. Does that help? Okay, other questions on this? Last chance. Questions about the exam or this example? Okay, so let's continue talking about Taylor and Maclaurin, which aren't specifically on the exam, but we're using lots of principles that are on the exam. So, and you'll have this for web work for Monday. And like I said, so still dealing with series, so it's lots of things that we've learned are involved in this. So let's try this one here. So there's kind of two aspects to these Taylor and Maclaurin series. There's building it from scratch. So we're going to actually find all of the derivatives. Okay, we're going to actually find all the derivatives. We're going to build a table, and we're going to build it term by term from scratch. And then there's an aspect to this where we have basic functions that we already know the Taylor and Maclaurin series for, and we can use those to build variations. Okay, so let's do one thing of each. So this first thing we'll do is we'll build the Taylor series for natural log of 2x centered about x equals 3. And so because it's not centered at 0, it's a Taylor series. If it were centered about x equals 0, then it'd be a Maclaurin series. Okay, so here's for this particular centering about 3, we're going to have the derivative, the nth derivative evaluated at 3 over n factorial times x minus 3 to the n. That's the Taylor series centered about 3. So here's our function, f of x, natural log of 2x. Okay, so the 0th derivative is simply natural log of 2x. The 0th derivative is the function itself. Centered at x equals 3 is going to be ln of, or taken at 3, ln of 6. Okay, now the first derivative is going to be 1 over 2x times 2. by the chain rule, right? 1 over 2x times 2, which gives us 1 over x evaluated at 3, 1/3. Check my math. Okay? Second derivative is going to be the derivative of that, which is going to be negative 1 over x squared. Right? Because it would be x to the minus 1. So it would be negative x to the minus 2. Evaluated at x equals 3 is negative 1/9. So this is negative x to the minus 2. What's the derivative? It's going to be positive it's going to be 2 times, right? 2 times 1 over x cubed, positive. Evaluated at 3, 2/27. Okay, what's this going to be? Now this is going to be 2 times x to the minus 3 is going to be negative 3 times 2 times 1 over x to the 4th. Evaluated at 3 is going to be negative 3 times 2 over 3 to the 4th. Okay, so I'm not writing out final answers because, or I'm not simplifying things because what we eventually want to do is get a formula for this. So that we can not only write out the terms of the Taylor series, but then write out in summation notation what this particular series is in summation notation. That would require that we get a formula for the nth derivative taken at 3. So that's why I'm gonna keep things multiplied out instead of, or keep things in their factored form, because then we can see the pattern for what the nth derivative is taken at 3. Okay, what are we going to get next? We're going to get positive 4 times 3 times 2 times 1 over x to the 5th. So what we'll get here is the same thing with 3 plugged in. Okay, now it'll be negative 5 times 4 times 3 times 2 times 1 over x to the 6th. And then we're going to plug 3 in. So do you see this list of coefficients here? What's emerging there? What do you see? So we'll do it one more time. It would be x to the negative 6 will give us positive 6 times 5 times 4. What is this? Well, yes, it is alternating. We got negative, positive, negative, positive, negative, positive. But what is 6 times 4 times 6 times 5 times 4 times 3 times 2? It's factorial. So in this formula for the nth derivative of taken at 3, we see a factorial forming. So the nth derivative is going to be what? So we have the alternating effect. When n is 1, we get positive. When n is 2, we get negative. So it's going to be n to the, or negative 1 to the what? When 1, it's positive. When 2, it's negative. When 3, it's positive. So we want n times negative 1 to the n plus 1. And then for the nth derivative, what factorial do we have? For the nth derivative, what factorial do we have? We have so if the derivative is 7, if n is 7, we have the n minus first derivative, or factorial. And then we always have 1 over 3 to the what? So this 1 over x to the 7th, 1 over x to the 6th, those 1 over 3 to the n. That's not multiplied. This is the nth derivative, right? So this the nth derivative taken at 3 has this formula, negative 1 to the n plus 1 times n minus 1 factorial times 1 over 3 to the n. That is the pattern that emerged as we started writing all these out. Now, where does n start at? So does that, when n equals 0, we have something totally different, a natural log of 6. So we're going to just keep that separate because that doesn't fit, that natural log of 6 doesn't fit this formula at all. So we've got to write that term separately. So this function is going to be natural log of 6, first of all, plus, and now n's going to start at what? 1, because this is what we got when n equals 0. And what was the nth derivative taken at 3? Negative 1 to the n plus 1. Times n minus 1 factorial times 1 over 3 to the n. That whole thing is what we found as the nth derivative taken at 3. Times x minus 3 to the n. So now this is just following the form of the Taylor series over n factorial. Okay, let me just pause for a second here. Do you follow what I'm doing? Anybody have a question? Ask if you're not sure. Okay, now can we simplify that? So is there anything in that that can simplify? The answer is yes. What is it? Bless you. Yeah, the factorials. Look, we have n minus 1 factorial in the top and n factorial in the bottom. So this is definitely fair game for the test. What does that simplify to? N minus 1 factorial in the top and n factorial in the bottom. Should know that. One over n, right? So what is n factorial? It's n times n minus 1 factorial. N times n minus 1 times n minus 2 times n minus 3. So that denominator is n times n minus 1 factorial. So those go away, just leaving n in the denominator. We could also, if we want, we could combine these. How, using laws of exponents. How do those group up together? So just over n, that's the, what about 1 over 3 to the n times x minus 3 to the n? What is that? X minus 3 over 3 all to the n. Okay, questions on, and then writing out the individual terms, that's kind of the easier part. Just do the math right. Don't do the math right, and you can just write out all the individual terms starting n equals 1, n equals 2, n equals 3. Okay, let's see this in the graph. So this is where it's interesting, how these Taylor series work. So last chance. Any questions on that before I erase it? So So instead of little n, I'm going to use k. My capital N is allowing me to choose different number of terms to select. Right now, I'm selecting 8 terms. But I'm going to go back and do this. Here we go. There we go. Okay, here we go. So here's n equals 1. So if we do ln of 6 plus the first term, we get that purple line. Okay, if we do the first 2 terms, notice centered at 3. So it's really good near 3, and then it's worse as we move away. So with each, as I increase capital N, I'm taking more and more terms of the polynomial of the series that we found. And with more and more terms, we do better and better at approximating the original function, the red one, centered at 3, and then with more and more terms, it gets better farther away from 3. So here's ln of 6 plus 10 terms of the Taylor series, doing a really good job from about 1 to 6, approximating that curve. Okay, study and get the help you need. See you Friday at 8:45.